Okay, today in class we whiteboarded the rest of worksheet 3 and started worksheet 4. The first one we looked at was number 3, looking at an Atwood's machine. And we're trying to figure out the acceleration of the system when the blocks are released. There's two methods that you can choose. One is you can choose just one system, and you would have a weight force A downward that's causing the acceleration, and there would be an opposing weight from WB um, that's in the exact opposite direction. The pulley changes the direction of that force. And then you can write a net force equation. Net force would be equal to WA minus WB. And the way you find the net force, it's mass times acceleration. So the mass of the system is 7 kilograms times A equals 30 newtons. Solve for the acceleration, you get 4.3 meters per second squared. And then we can go ahead and figure out how much time it would take, and that's using kinematics. And we use delta y equals 1/2 a t squared. Plug in, and we get a time of 0.97 seconds. Another way that you could do it is you could use a two-system approach and draw free bodies for both A and for B. There would be tension forces upward on both of them, and those are equal in magnitude because the pulley is massless. We have a WA force downward that's bigger than the tension, and a WB force that's downward that's smaller than the tension. We can then write two net force equations. F net of A equals WA minus tension because it's accelerating downward. F net of B would be equal to tension minus WB because it's accelerating upward. That's why you do that particular order. You can plug in or solve it for t and then plug into the other equation. So F net equals WA minus the quantity F net B plus WB. So we plugged in what tension is. Then we can substitute in the mathematical models for F net and for weight and solve it, and we get 4.3 meters per second squared, just like the other approach. And then we can use kinematics to solve the rest of it. Delta y equals 1/2 a t squared, and solve this, and we get 0.97 seconds, just like the other approach. Students need to know how to do both approaches. So pick your favorite approach, perfect it, and then start doing the other one. Then we looked at the next problem on the next page, and this is looking at a modified Atwood's machine. Notice the Atwood's machine is actually two objects on a pulley, and you just one's going up, the other one's going down. This is modified Atwood because we have horizontal motion and vertical motion. Okay, the first question, which system has the greatest net force? Well, what's causing the acceleration? It's the falling mass. And so therefore the greatest net force would be system C because it has the greatest proportion of the weight that's unbalanced. Which system has least inertia? Inertia is a measure of mass, laziness, and the least inertia would be system A. Determine the acceleration for each of these. Well, first of all, we need to know that A is proportional to F net over m, just like we found in the lab. And then we need to look at each of these. Well, for system A, treating everything as a system, there would be one force mg downward. And then, of course, acceleration would be equal to F net, which is that mg, divided by the mass, which is 2m. So we get g over 2. Okay, then for system B, same thing. We have mg downward. And this time, you still have the mg being the net force, but now the mass is 3m, so it's g over 3. And for system C, now we have a net force of 2mg. So A equals 2mg divided by the total inertia, which is 3m, and we get 2/3 of a g. For number 4, it says find the tension in the the tensions in the rope is 14 newtons. Find the acceleration. I'm going to treat everything as the system, so the entire train. So we would have a weight force down, a support force up, and a tension force kind of upward at an angle. F net then would be equal to the x component of the tension. and net force is ma, and that's going to be equal to 14 times cosine of 60, and we get an acceleration of 0.777 meters per second Part B, what is the normal force on the 3 kilogram car? Now my system's going to be the 3 kilogram car. So the free body diagram of it looks like this. Then the support force plus the y component of the tension is going to be equal to the weight because it's not having any accelerated motion vertically. Okay, then we can plug into this and solve for that support force, and we get 17.9 newtons. Part C, what's the tension in the string between the first two cars? I'm going to choose my system to be the 4 kilogram and the 2 kilogram mass. So this would be my free body diagram. Support force up, weight force down, and a tension force to the right. My net force equation would look like this. F net equals the tension. And plug into this, the net force would be ma. The total mass is 6 kilograms times the acceleration we found up above, 0.777. Plug in, we get the tension is equal to 4.67 newtons. Part D, what is the tension in the string between the last two cars? This time I'm going to choose my system to be the 4 kilogram object. And there's my free body diagram for it. Support force up, weight down, tension to the right. My net force equation would be the tension. Plug in F net equals ma. Plug in that, and I get tension is equal to 3.11 newtons. Part E, what is the normal force that the 2 kilogram car experiences? My system now is going to be the 2 kilogram car, and that's the free body diagram for it. All I care about though is the support force, N. So N equals W, and so that's 20 newtons. Number 5. For this, we're trying to figure out the acceleration of the blocks. So my system is going to be both blocks, and this would be the free body diagram for it. For this, the net force would be equal to the y component of the force that's at an angle minus the weight. Plug into this, F net is equal to 2 times A because it's a total mass of 2 kilograms. The y component's given by the cosine of 30 degrees times 25 newtons, and then minus the weight of 20 newtons. And finally solving, we get the acceleration to be 0.83 meters per second each second. Part B, what is the normal force on the 1.8 kilogram block? So now the normal force is going to be equal to the x component of the applied force. So the support force is going to be 25 times the sine of 30 degrees, which is 12.5 newtons. Part C, what is the tension of the string? For this, my system now is going to be the 0.2 kilogram mass. So I have a tension force up that's bigger than my weight. My net force is equal to tension minus weight. Net force is equal to ma, so the mass would be 0.2 times the acceleration I found up above, 0.83. And the weight is 2 newtons, so solve this and I get 2.167 newtons. Okay, the last problem that we whiteboarded was number 1 of worksheet 4. This is a roller coaster, and we're asked to draw a free body diagram for the car and the riders. Notice it says that friction is ignored. So for this, we'd have a support force and we'd have a weight force. Part B, determine the value of the component of the force of gravity parallel to the hill. Well, I'm actually going to write a net force equation. F net is equal to Wx. And the Wx would be given by 3,000 newtons times the sine of 65 degrees, which would be 2,719 newtons, which is the answer for part B. Part C, what is the acceleration of the roller coaster? F net equals ma, so I'm going to plug that in and solve for acceleration, and I get 9.06 meters per second each second. And then part D, if they're traveling 4 meters per second at the time shown in the picture, how fast are they traveling at the end of the stretch was 20 meters later? This is kinematics. So Vs squared equals Vi squared plus 2AD. Plug in, and I get 19.5 meters per second.